Okay. So, in the previous lecture we have started network equation, we came up to equation 252, but again to begin with we are starting from the scratch, from the beginning, that referring to your figure 26, the machine terminal and infinite bus voltages in terms of the D and Q components are, that is E t tilde is equal to E d plus J E q, this is equation 248, and E b tilde is equal to E b d plus J E b q, equation 249. So, let us go to figure 246, right. So, this is your figure 26. So, this is your figure, this E b is the reference, right. So, from here we can make out that this is my E t, this is my E t, right. So, and E t is equal to E d plus E t is equal to your E d plus J q, right. Similarly, another thing if you see that E b is equal to your, this is your direct axis component, that is E b d plus J E b q, right. So, this is my E b q and this is my E b d, right. And another thing is that E b q is equal to, because these things later we will need, that E b q is equal to E b cos delta, E b cos delta, right. Similarly, E b d is equal to your E b cos 90 degree minus delta, that means your sin delta, because this is delta. So, this angle is 90 degree minus delta, right. Similarly, if you look about E q will be E t cos delta I, and small e q and small e d will be your, what you call that, E t your cos 90 degree minus delta I. So, E t sin delta I, right. So, this is your figure, this thing and your this thing and this thing and this thing these have been used for the derivation of those equations, right. So, let me clear it. So, let us write. So, E t tilde is equal to E d plus J E q and E b tilde E b d plus J b. The network constant equation for the system of figure 23b, that means that Thevenin equivalent one, right. E t, then x t, your x c all are given, and E b is that your infinite bus voltage, the Thevenin voltage, right. Therefore, from that figure, we am not going to that figure is understandable to you. So, E t tilde will be E b tilde plus R e plus J x e I t tilde, right. So, E t tilde E d plus J e q and E b tilde E b d plus J b q, and R e plus J x e and I t tilde is I d plus J i q. This is equation 250. If you multiply this, second term, right, and your collect real and imaginary, collect real part and imaginary part, then E d will be equal to R e I d minus capital X e I q plus capital E b d. This is equation 251, and E q will be R e I q plus X e I d plus E capital capital E b q. This is equation 252, where just we have given that E b d is equal to E b sin delta and E b q is equal to E b cos delta. This is equation 253 and 254. Now, using equation 246, 247 to eliminate E d E q in equation 251 and 252, and using the expression for psi a d and psi a q given by equation 240 and 244, we get, listen, I mean just hold on. Thing is that this derivations, actually this derivation, that using equation you use 246, 247 to, you have to eliminate E d E q in equation 251 and 252, and using the expression for psi a d and psi a q given by 240 and 244, you find out the solution for I d and I q. There is no need to remember this, but question is that I suggest you please derive it. If I give all the derivations here, then it will consume more time, but no need to remember, but you please just of your own, whatever has been said, everything, I believe everything is a correct one. If you find any typographical error or anything, you just my writing error, you please let me know, right. I can rectify myself, but I believe all these things are okay. And just to derive and find out an expression ID and IQ, because we need small perturbation thing. So, ID is a function of x t q, it is equal to x t q in bracket psi f d in bracket LADS upon LADS plus LFD minus EB cos delta, bracket is closed, minus RT EB sin delta divided by D. What is D will give, right. Similarly, IQ will be RT psi FD LADS upon LADS plus LFD minus EB cos delta plus your XTD EB sin delta, right, divided by D. One D is here, right. So, because we need small perturbations, and these equations actually your what you call your expression are very lengthy, right. So, once you get this, after making this mathematical manipulation ID and IQ, this is equation 255, this is 256. Now, all the I have to give the term XTQ, then your RT, then D, all these terms. So, RT is equal to RA plus RE, right, and that is R total is equal to your RA plus RE, right, and XTQ will be XC plus LAQS plus LL is equal to XC plus XQS, because in per unit system I told you inductance and reactance are same. So, this term, that is your XQS is equal to LAQS plus capital L small l suffix, right. So, that is why this term is XQS. Similarly, XTD is equal to XC plus bracket LADS dash plus LL is equal to XDS dash. So, XDS dash actually is equal to this term your LADS dash plus your LL, right, because in per unit inductance and your reactance they are same. Similarly, D is equal to RT square plus XTQ into XTD. These expressions are not difficult one, just put one after another and get those expressions. This is equation, all this equation collected together. So, total is given 257. The reactances, your XQS and XDS dash are saturated values. In per unit, they are equal to the corresponding inductances that I told you. Now, we have to find out the linearized system equations. So, expressing equation 255 and 256 in terms of perturbed values, we may write, that is equation 255 and 256, that is this equation 255 and 256. You take the small perturbation value, that delta ID is equal to find out perturbed value and delta IQ, you know the perturbation thing, right. So, if you do so, it will come in this form, that delta ID will become say M1 into delta delta plus MT into delta psi FD. Actually, in equation 256 and your 256 and 255, right. So, two variables are here, one is psi FD, another is delta, right. Here also psi FD delta, other things are constant. So, that means if you do so, it will be in this form, delta ID is M1 delta delta plus M2 delta psi FD, in this form will come. This is 258 and delta IQ will become N1 delta delta plus N2 delta psi FD, this is 259. Now, when you do the small perturbation thing, then what is M1 M2 and N1 N2? M1 will become EB into X TQ sin delta 0, because around an operating point delta 0 you are taking the perturbation, right. I mean delta tends to your delta plus delta 0, right. So, M1 will become your XTQ sin delta 0 minus RT cos delta 0 upon D, right. Similarly, your N1 will be EB RT sin delta 0 plus XTD cos delta 0 by D. Similarly, M2 is equal to XTQ upon D LADS upon LADS plus LFD, and N2 is equal to your R2 by D LADS upon LADS plus LFD. Collecting all these things, this is we have marked as equation 260. Therefore, small perturbation model, small perturbation expression for ID and IQ, like delta ID is this one and delta IQ is this one. This is 258 and 259. I suggest you do this thing, otherwise this derivation if I put it here, it will never, it will be an unending story then, right. So, you please do it, once, and just you can remember m1 delta delta, m2 delta psi f d, n1 delta delta. If anything is given, m1 m2 n1 n2 will be supplied rather than computing, because I know it is difficult to remember all sort of things, right. So, by linearizing equation 242 and 244 and substituting in them the above expression for delta psi d and delta I q will get. So, you have to linearize equation 242 and 244 for psi d and psi q. So, here just hold on, equation you have to linearize again 242 and 244. So, I think it will be here only, that is expression for this thing, just hold on, that is your this is 236, just hold on, this is 242 and 244. So, this is 242, that this equation for psi a d you have to again take small perturbation, this 242 and this is 244, these two equations you have to take the small perturbation 242 and 244. So, if you linearize now that equation 242 and around some operating points and substituting in them the above expression for delta I d and delta I q, you will get that your delta psi a d will become L A D S dash bracket minus delta I d plus delta psi f d upon delta your L f d, right, or delta psi a d will become 1 upon L f d minus m 2 bracket close L A D S dash delta psi f d minus m1 L A D S dash delta delta. This is equation 261. Basically, what you have to do is you substitute the expression for delta I d from this equation, right, and m1 m2 are given, m1 your what you call m1 and m2 are given, this is m1 and this is m2, right, all are given. So, if you do so, it is becoming in terms of m1 and m2. So, delta psi a d is 1 upon L f d minus m2 L dash A D S delta psi f d minus m1 L A D S dash delta delta. This is equation 261. Similarly, for this one if you take, that is linearize equation 244. So, it will actually this equation is you are linearizing equation 244, this equation you are linearizing, that is your 244, that is your because there it was given psi a q is equal to minus L a q s I q. So, it is delta psi a q is equal to minus L a q s delta I q, and delta I q we have got it. So, just what you do is that you substitute, right, that you substitute for delta I q, it is simply only multiplied by L a q s, this is your delta psi delta I q, right, this one you substitute and your what you call, and this is your minus n 2 L a q s delta psi f d minus n 1 L a q s delta delta, this is equation 262, right. Now, linearizing equation 241 and substituting for delta psi d from equation 261 gives. Now, you have to linearize equation 241. So, before doing this we will go back to this equation 241, that is your this equation, that field current equation, this one also you linearize, right, you just linearize this equation, because delta I f d will be delta psi f d minus delta psi a d upon L f d, right. Therefore, you linearize equation and substituting for delta psi a d from equation 261, right. So, delta I f d then delta psi f d minus delta psi a d divided by L f d, and this expression for delta psi a d, I mean this equation 261, this delta psi a d you substitute here, if you do so, you substitute here, you will get it is delta I f d is equal to 1 upon L f d in bracket 1 minus L a d s dash upon L f d plus m 2 L a d s dash into delta psi f d plus 1 upon L f d m 1 L a d s dash delta delta. This is equation 263, right. So, then again you linearize the form of equation 245, that is the torque equation you have to linearize. You go to 245 rather, where the torque equation T expression is given, and that one also you linearize around some operating point, say I d 0 and I q 0 and psi d 0. So, you will get delta T is equal to psi d 0 delta I q plus I q 0 delta psi a d minus psi a q 0 delta I d minus I d 0 delta psi a q, just you take the small perturbation, right, in equation 245. So, I am not going to the expression again, but just when you listen to this video, just keep those equations and just try yourself once, only once, right. So, now in this expression you substitute for delta ID, that is from equation 258, delta IQ from equation 259, because all these things are given before, right, and delta psi AD from equation 261 and delta psi AQ equation 262. That means you substitute here delta expression for delta IQ from equation 259, then substitute for delta psi AD from equation 261 and substitute for delta ID from equation 258 and substitute psi AQ from equation 262 and simplify. Then you will get in this form that delta T will be K1 delta delta plus K2 delta psi FD. This is equation 264, right, because in our synchronous machine model we will in the case constant we will try to develop the model. There are 6 constants, say K1, K2, K3, K4 and K5, K6. So, now it is K1 and K2. So, delta T will be K1 delta delta plus K2 delta psi FD. This is equation 264, right, where if you substitute and simplify, your K1 will become N1 into psi AD0 plus LAQS ID0 minus M1 in bracket psi AQ0 plus LADS dash IQ0. This is equation 265, right. Similarly, your K2 will be N2 psi AD0 plus LAQS ID0 minus M2 in bracket psi AQ0 plus LADS dash IQ0 plus LADS dash upon LFD into IQ0. This is 266. These are your what you call, these are your expression for K1 and K2, right. So, in otherwise how one can find out the K2? For example, suppose psi FD is constant, suppose you want to find out K1, suppose psi FD is constant, that means delta psi FD becomes say 0. For example, if psi FD is constant, in that case Q1 will be equal to delta T upon delta delta. Similarly, if your delta is constant, then your K2 will be delta T upon delta psi FD, right. So, now by linearizing equation 235, 236 and 237 and substituting the expression for delta IFD and delta TE given by equation 263 and 264, we obtain the system equations in the desired form, right. So, you have to linearize equation 235, 236 and 237. So, I will go to that 235 once again 235, 236 and 237, right. So, this is your what you call, just hold on, this is equation 235, already we have linearized it and I have shown it, right, and 236 also has been linearized and shown because the previous block diagram in terms of H, right, and your what you call omega 0 other thing, this all these things has been linearized. P delta omega I told you how to linearize this one. P delta omega will be 1 upon 2 Hs delta T m minus delta T minus K D into delta omega, and why it will depend I have shown you already. Similarly, P delta delta omega 0 delta omega r. So, P delta delta also will be equal to omega 0 delta omega r, because delta omega r is equal to omega r minus omega 0. This already we have discussed. And 237, right, and 237 you have to linearize, this is 237 also you have to linearize here. So, this is basically P delta psi FD is equal to this one delta EFD minus omega 0 RFD delta IFD. So, all these things expression for your what you call, all these things you have to put together in that differential form, right. So, those things little bit I suggest, I am giving the final expression because it takes long time to this, but you try once, right. So, if we do so, that is a linearizing equation 235, 236 and 237, and you substitute the expression for delta E, I show you delta T given by the equation 263 and 264, we obtain the system equation in the desired form, right. That means in that your differential form, the derivative form. So, this will be equal to delta omega dot delta delta dot and delta psi FD dot, because it is P delta omega r. So, P is d dt. So, it is delta omega dot. Similarly, for delta delta dot, similarly for this one we put in this form that A11 A12 A13 A21 0 0 0 A32 A33 and delta omega delta delta state variable form we are putting delta psi FD plus BU form, that B11 0 0 0 and 0 B32 delta Tm delta EFD. This is equation 267, right. So, later you will see sometimes I have used this is A31, right. A31 actually is equal to 0. Sometimes for generalizing the expression I have written A31 delta omega r, but unless and until stated you have to see that A31 actually is equal to 0, right. So, where now when you make all this, your A11 will become minus Kd upon 2h, A12 will become minus K1 upon 2h, A13 will become minus K2 upon 2h, A21 will become omega 0 is equal to 2 pi f0, and A32 will become minus omega 0 RFD upon LFD M1 into LADS dash. When you do all these things and putting in this form, so ultimately this is the your non-zero elements of A matrix, right. And similarly for non-zero element of B matrix, that is B11 and B32. So, A33 is also there, minus omega 0 RFD upon LFD. This is your here is A33 is there. So, this is your minus omega 0 RFD upon LFD in bracket 1 minus LADS dash upon LFD plus M2 LADS dash, right. And B11 will become 1 upon 2h and B32 will become omega 0 RFD upon LADU. This is equation 268, all these things, right. So, this is basically, if you look into that, this is basically a now 3 into 3 matrix, right. At present it is 3 into 3 matrix, and state variables are delta omega r, delta delta and delta psi FD, right. Now, and delta Tm and delta EFD depend on prime mover and excitation controls. With constant mechanical input torque, if it is constant, then delta Tm will become 0. Similarly, with constant exciter voltage, delta EFD will become 0, right. If Tm is constant, then delta Tm will become 0, and if EFD is constant, that exciter output voltage, then delta EFD will be 0, right. Now, block diagram representation. So, now once we have developed this equation, this is not required, this is from my reference. The figure 27, I will show you that, shows the block diagram representation of the small signal performance of the system. In this representation, the dynamic characteristic of the system are expressed in terms of called the K constant. I told you, so we will find out there are 6 K constant, K1, K2, K3, K4, K5, K6. Till now we have made a K1 and K2, slowly and slowly will develop, right. So, with this constant K1 figure 27 will go, right, and this your I will show you figure 27, but from equation 264, that is we may express the change in air gap torque as a function of delta delta and delta FD as follows. This is we have developed delta T is equal to K1 delta delta plus K2 delta psi FD, right. Now, where K1 can be written as delta T upon delta delta with constant psi FD. If psi FD is constant, then delta psi FD will be 0. So, in that case K1 will be delta T upon delta delta. Similarly, K2 will become delta T upon delta psi FD with constant rotor angle delta. If rotor angle delta is constant, then delta delta will be 0. Therefore, K2 will be delta T upon delta psi FD. This is the meaning of these two terms K1 and K2, right. Now, the expressions for K1 and K2 are already given in equations 265 and 266, right, but this is another way of determining your K1 and K2. Now, the component of torque given by K1 delta delta is in phase with delta delta. This meaning we will see later. The component of torque given by K1 delta delta is in phase with delta delta and hence represent a synchronizing torque component. So, why it is in phase next will come after some time, and that is and there also I will put a question to you, that question you should give an answer. First let me show it, right. So, component given by K1 delta delta is in phase with delta delta and hence represent a synchronizing torque component, right. So, we will come to that, and the component of torque resulting from variation in field flux linkage is given by K2 delta psi FD. That means when we will come to the block diagram, right, that figure 27 we have not come. So, I will go back again. This is my figure 27 in terms of your K1 and K2. So, earlier we have seen that your this block diagram, you bring that your kd delta omega term to the left hand side and simplify, you will find this is delta Tm positive, this is minus delta Te, and it is 1 upon 2 Hs plus kd, then here it is output is delta omega r, and delta delta will be delta omega r, omega 0 upon s, this already shown. And from delta delta, that your what you call that two terms are there for delta T, one is k2 delta psi fd, another is your k1 delta delta. So, if you look into the block diagram, when you make the block diagram, right, when you make the block diagram, that there you see that delta T is nothing but your k1, rather first I am writing this one, delta delta plus k2 delta psi fd, right, and delta psi fd also related to your what you call that your this k4 term, right, and k3 and one sorry, and another k3 term that we will see later, right, but this is your figure 27. So, we will go back again. The component of torque given by k1 delta delta I told you is in phase with delta, we will come to that later, and hence represent a synchronizing torque component. The component of torque resulting from variation in field flux linkage is given by k2 delta psi fd, right. The variations of delta psi fd is determined by the field circuit dynamics, that is third equation of equation 267, right, that is the third equation of 267, the state variable equation we have written, and this is actually third, that is P delta psi fd, that if you write A32 delta delta plus A33 delta psi fd plus B32 delta fd, that means this equation, right. When you come to this thing matrix 1, right, this equation, that delta psi fd dot is equal to your A32 delta delta plus A33 delta psi fd plus B32 delta fd from this equation 267, right. So, same thing we are making it here, the third equation we are writing, that your P delta psi fd is equal to A32 delta delta plus A3 delta psi fd plus B32 delta fd, right. Now, delta psi fd can be we put in this form. What you do is this term you bring it to the left hand side and simplify the way it has been made here, bring this term, and here you make it your what you call that your B delta EFD term is there, right, and A3 to delta delta. You what you call that you bring this term and simplify this one and bring in this form, all the K3 and K4 are given. You please bring it in this form, right. That is why I mean just you have to simplify this, and you simply it will become delta EFD minus K4 delta delta. So, now question is that your that K3 and K4 are given like this, K3 is equal to minus B32 upon A33, K4 will become minus A32 upon B32, you just represent in this form, and P is nothing but differential operator in S domain, we will put S, that is all, right, and T3 is minus 1 upon A33 is equal to, it can be shown that it is K3 TDO dash into LADU upon LFFD. This is for you, this is a small exercise for you, that how T3 is coming, this is a small exercise for you, just see the book, right, and just find it out. So, this is a small exercise for, and P is nothing but differential operator, that will take always S, right, that is written replacing P by S, right. So, we thank you very much, we will be back again.